Separable equations. A separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. So to get a picture of what that looks like, we're just going to do some examples, okay? So what we can do is when you can separate an equation like this, you're able to get all of the y values with the dy and all of the x values with the dx. That's what you're able to do for these type of equations. So if we try to do that, let's to solve this, what we're going to try to do is get all the y's with the dy and all the x's with the dx. So I can do that by multiplying both sides of this equation by 4y cubed. So I can get 4y cubed dy. At the same time, I can multiply both sides of this equation by dx, and that would give me e to the 2x dx. And I was able to separate the x values from the y values. And once we have this, then we can integrate on each side. So let's integrate on each side. And so when I integrate the left side, I get y to the 4th divided by 4 times 4. I just get y to the 4th. On the right, if I integrate e to the 2x, you could use a u substitution, but it's going to become a 1/2 e to the 2x plus a constant. Let me just make sure I didn't mess that up. I would let u be 2x. I would let du be 2 dx. I would say 1/2 du is dx. I would say 1/2 du gave me the dx, and this is just e to the u. 1/2 e to the u. 1/2 e to the 2x. Okay, I'm good with that, plus a constant. So this is what we get right here. Now, to solve for y, we need to take the 4th root. So this is going to be the 4th root of 1/2 e to the 2x plus a constant. And that constant will be underneath the root there with the y. All right, example 2. So what is the solution to a differential equation? It is a function that you could plug it and its derivatives into the given differential equation, and it would be true. So find the solution to this differential equation that satisfies the given initial condition. So this time they give us an initial condition we have to meet. So with an initial condition, what we can do is solve for that constant right there. That's what we could do. So let's see. Is this a separable differential equation? It will be. We can multiply both sides by dx. So if I do that, I get dy is equal to 7x e to the y dx. And if I want the y's over here, I can divide both sides by e to the y, which would be e to the negative y dy is 7x dx. Then we can just simply integrate each side. If I integrate the left side, I'm going to get negative e to the y is equal to 7/2 x squared plus a constant. I can divide both sides by -1. E to the y is going to be negative 7/2 x squared minus c. Then I could take the natural log of both sides of this, giving me y is equal to the natural log of negative 7/2 x squared minus c. And I'm just going to leave it like that right there. All right. The third one, solve dz dt plus 6 e to the t plus c is 0. Okay, so to separate this it's not immediately obvious, but what we can do is I'm going to move this term over to the right. dz dt is equal to negative 6 e to the t plus c. But that can also be written as negative 6 e to the t times e to the z, if you remember your exponential rules. I'm going to multiply both sides of this by dt. I'm going to divide both sides of this by e to the z, and that will separate it out. So on the left, I get e to the negative z dz. On the right, I get negative 6 e to the t dt, and then I can integrate each side. So on the left, to integrate, I get negative e to the negative z. On the right, I get negative 6 e to the t plus a constant. To solve for my dependent variable z is what I need to do. I'm going to divide both sides by negative 1. I'm going to take the natural log of both sides. And then I'm going to divide both sides by negative 1. So I get that z is equal to negative the natural log of 6 e to the t minus c is a solution to this differential equation. All right, example 4 goes like this. We have du dt is equal to 2t. This is supposed to be a secant. I don't know what happened there. Squared of t over 2u. With the initial condition, oh, wait. Somewhere I missed an initial condition. Oh, example 2. I'm sorry. I was supposed to solve for c. So let's solve for this initial condition. Y of 0 is 0. So we say 0 is equal to the natural log of negative 7 over 2, 0 squared minus c. All right. So 0 is equal to the natural log of 0 minus c. We know that the natural log of 1 is 0. So negative c needs to equal to 1. So c is negative 1 is what we get right here. So if c is negative 1 with the initial condition, y equals to the natural log of negative 7 over 2 x squared plus 1 is what we get right there. I'm sorry, I forgot to do the initial condition part right there. Alrighty, let's continue with example 4. What we have here is a separable differential equation. To get the u's on the same side, I'm going to multiply both sides of this by 2u. I get 2 times u du is equal to 2t plus secant squared t dt. All right. On the left-hand side, we can integrate. On the right-hand side, we can integrate. So, let's see. The integral of 2u would be 2u squared divided by 2, or just simply u squared. On the right, the integral of 2t would be 2t squared divided by 2, or just t squared. Plus, the integral of secant squared is tangent of t plus a constant. Okay. U is equal to plus or minus the square root of t squared plus the tangent of t plus a constant. However, we were given this initial condition, which says that when t is 0, u is negative 6. So let's think about this for a second. The square root of something, and we're talking about real numbers here, is going to be a positive number. The square root of anything is going to be a positive number. And if we need it to be negative, I'm only going to look at, I'm going to disregard this positive because we need it to be negative 6. So we're not looking at this. So u is going to be negative. Negative 6 is going to equal to the negative of 0 squared plus the tangent of 0, which is 0, plus c. So negative 6 is equal to negative the square root of c. So 6 is square root of c. C is 36. That's what we get right here. So what function will satisfy this differential equation with the initial condition? It will be u, or u of t, if you want to write that, is equal to negative the square root of t squared plus the tangent of t plus 36. All right, now for a couple of applications. Okay, so here we go. These are mixture problems, and they result in having to solve a differential equation. So this is good. It says a tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt is in the tank after t minutes? How much salt is in the tank after 20 minutes? So what we need to find basically is how much salt is in the tank at any time t. And if we know that, we can answer the same question. So the problem is, what is this? So I'm going to say, let's let A of t represent the amount of salt in the tank after t minutes. Now, the amount of salt is going to be in kilograms. Okay, and t is in minutes. All right, that's what A is. So, to do a mixture problem like this, I always draw like a little picture. Here's my tank. It's got 1,000 liters in it. It's got with 15 grams of salt mixed in there. Okay. Then we're looking at something pouring into the tank. Pure water is coming into the tank. So here's the N, and it's water. So this has got 0 kilograms of salt because it's water is coming into the tank at a rate of 10 liters per minute. This is N. And then exiting the tank, it's being thoroughly dissolved and then drains out. And what's coming out is a mixture, but it's being drained at the same rate. So it's coming out at 10 liters per minute. So a good way to approach these mixture problems is to consider the change of rate of the amount of salt. So what is the change in rate of the amount of salt, dA dt? Well, that's going to equal to the rate of the salt in minus the rate of the salt out. Rate in minus rate out. Okay. Well, and so what would these units be? A is in kilograms, T is in minutes. So this will be in kilograms per minute. Okay, so the rate in is going to be how much salt we have in times the flow rate, right? So the flow rate is 10 liters per minute. Okay, and how much salt do we have coming in? We have 0 kilograms per liter coming in because it's water. The rate out, however, is going to be, the rate out is still, it's flowing at the same rate, 10 liters per minute. But what is the concentration of salt exiting the tank that's being mixed up? We don't know. It's going to be the amount of salt, A, at any time t, A of t, right, per liter times that. So this is the equation that we get. We get that dA dt. So let's check the liters will cancel out. So this is going to be in kilograms per minute, right? Which is what we expected. It's going to equal to 0 minus 10A. This is a differential equation that we come up with right here. So we need to solve this right here. And when we do, hang on just one second. Let me orient myself. I'm looking at the wrong thing. Okay, let's just keep going. We're going to solve this right here. Okay, so what we get here something's bothering me a lot. Oh, this is what's bothering me. Not per liter, but per 1,000 liters. That's what was bothering me. That's what was off right there. So let me fix that. Thank you for your patience. So what I get here is negative 10 divided by 1,000, which is over 100. So this is really a 0.01. Okay, this is the differential equation that we're solving right here. So I like that a little bit better. I think that's better. So to solve this guy, Okay, so what we find is that we have it results in a separable differential equation. So I can get all the a's on one side and the t on the other side. So I'm going to divide both sides by negative 0.01a. And when I do that, I get dA over negative 0.01a is equal to 1 times dt. Okay. So if I want to rewrite the 1 over negative 0.01, you can write that as negative 100 dA over A is dt. And we can integrate each side, which gives us negative 100 times the natural log of A. You can put absolute value signs on, but we don't actually need them because we're assuming that the amount of salt is positive, is equal to t plus a constant. All right, now to solve for A, we can divide both sides by 100. Okay, so we get the natural log of A is negative 0.01. I just put it back over there. T, and I can still say plus some constant t. We can, or C1 if we want to call it that. We can raise both sides by e, and we can get that A is equal to e to the 0.01 t plus some constant. But we can also write this as, this is e to this times e to that, and we could call the e to the C1 another constant, so we could call that, this is familiar to us, A of t is equal to A sub 0 is what I'm going to call that constant, e to the 0.01 t. Because this will be our initial condition. Did we have an initial condition? We did. Right here, at the beginning of this process, when time is 0, A of 0, how much salt was in the tank? At the beginning, there were 15 kilograms of salt when time is 0. So we can use that and substitute that. We say 15 is equal to A sub 0 e to the 0.01 times 0, and get that A sub 0 is 15. So our equation with this initial condition that describes the amount of salt in the tank at any time t will be 15 e to the negative 0.01, did I lose my negative right there? Okay, negative 0.01 t is our answer right there. So if we needed to know how much salt is in the tank after 20 minutes, we would just simply plug in 20, and when you do the math, you find that it's about 12.3 kilograms of salt. All right, one last problem here. A vat with 5,000 gallons of beer contains 4% alcohol. Beer with 6% alcohol is pumped into the vat at a rate of 5 gallons per minute, and the mixture is pumped out at the same rate. What is the percentage of alcohol after an hour? Okay, so to do this one, again, we have some tanks on that, and it's got 500 gallons of beer with 4% alcohol. Okay. And then it says beer is pumped into the vat with a slightly higher alcoholic level, 6% alcohol. It's pumped in at a rate of 5 gallons per minute, and then it's pumped out at the same rate after it's been thoroughly mixed, okay? So it's pumped out at 5 gallons per minute. So this is in and this is out. So again, this is one of those mixture problems, and it's good to look at the change of rate of the amount of alcohol, or we could look at it as the percentage of alcohol at any time t. So let's let A of t in this case, and let me separate out, this was the last problem. It represent the amount of alcohol amount of alcohol at time t. Okay, so this will be t in minutes. And we'll say the amount of alcohol will be in gallons, okay? And then we can work out the percentage here in a second. So let's look at the change of rate of the alcohol. dA dt, the change in rate of the amount of alcohol at any time t is going to be equal to the rate in minus the rate out. So we can look at it in percentages. So let's see. If we do that, what is the percentage of the amount of alcohol coming in? That's going to be at 6% alcohol coming in times 5 gallons per minute minus the rate out. So if we're doing it in percentage, we have to say, okay, it's the amount of gallons of alcohol, right? A of t, but we must divide that by the amount of gallons in the tank, 500 gallons, right? And times the rate going out, 5 gallons per minute. All right. So this keeps us consistent in percentages. Now, was there initial conditions? There was. The initial condition was that the amount of alcohol in the tank at the beginning was equal to 4%, 0.04 of the amount of gallons, 500 gallons. So 0.04 times 500 gives us 20. There were 20 gallons initially. I will just take note of that. All right, now let's go on with this. We get dA dt is going to equal to 6% or 0.06 is what we'll put here. So let me just do that, 0.06. That'd be better. Times 5 gallons per minute gives us 0.3 minus 0.01a. And this is a separable differential equation. So if I separate this, I get that dA over 0.3 minus 0.01a is equal to dt. If I integrate both sides, on the right-hand side, I get t plus a constant. On the left-hand side, I'm going to use a u substitution. U will be 0.3 minus 0.01a. du will be negative 0.01 dA, and then I can solve for dA, negative 100 du. So if I integrate here, I'm going to get the integral of negative 100 du 1 over u. Negative 100, the natural log of u, or negative 100, the natural log of 0.3 minus 0.01a. All right, this is what I get here. I can solve for a by dividing both sides by 100. So the natural log of 0.3 minus 0.01a is equal to t, negative t over 100 minus c over 100. I can raise both sides by the base e and get that 0.3 minus 0.01a is equal to e to the negative t over 100 times e to the negative c over 100. But I can call this my constant. I can say this is really a c to a power right there. So if I decide to, if I want to call this c or a sub 0, I'll just call it c. E to the negative t over 100. I've just rewritten it, this constant as this big C, minus 0.3. And then I'm going to solve for a by dividing both sides by negative 0.01. So I get a, or a of t, is equal to negative 100 C e to the negative t over 100 plus 30, because negative 0.3 times negative 100 is plus 30. Now, we do have an initial condition, which was that at time 0, A of 0 is equal to 20 gallons of alcohol. So, by solving, 20 is equal to negative 100 C e to the negative t over 100 plus 30. Subtract 30. Oh wait, what was t? T was equal to 0. This is a 0 at this point, sorry. 0. Okay, so what does that do to this? This becomes a e to the 0 or a 1. Let me clear that up. So this is really a negative 100 C times a 1. So C is going to equal to negative 10 divided by negative 100, or 10 over 100, or 1 over 10 is what C is equal to. So here we go. Our function A of t will be negative 100 divided by 10, or negative 10 e to the negative t over 100 plus 30. This is our function that describes how much alcohol in gallons there are at any time t. So if we want to know how much there are after 1 hour, since our units are in minutes, we take A of 60, and if we plug that in, we get 24.5 gallons. And if we want to know the percentage, we take 24, oops, I transposed those, didn't I? 24.5 divided by 500 gallons. And we see that the percentage of alcohol after 1 hour is 4.9% after an hour. So that's how you can do that type of problem.